Okay, welcome to Module 3. This is going to be Lesson 3.1, Force System Resultants, Part 1. We're going to start talking about moment. In this lesson, we're going to determine the moment of a force about a point in 2D using a scalar approach. Then we're going to determine the moment of a force about a point in 3D using a vector approach and the cross product idea. And then we're going to determine the moments of a force about an axis using a vector approach, and that's going to use the cross product and the dot product. Now, we haven't had moments yet, and that's because we were dealing with equilibrium of a particle. And equilibrium of a particle, it's a tiny little dot, and all the forces are either pointing towards it or away from it. And so what that means is there is no moment, no torque, as you've been calling it probably all these years before this. But as we move into the concept of a rigid body, something that is big enough that its size affects the system, then we're going to have the potentials for moments. And that's because the rigid body is so large that the forces can be acting in different locations on the free body, and thus having distance between them, perpendicular distance, lever arm, moment arm, there's all these different terms for it, but that's what's going to cause the moment. So here's a good example. We have a race car here, Formula 1 car, and it's, this is by no means a complete free body diagram. I just wanted to give you something that some of you might find interesting. And so these are some of the forces I came up with. There's a downward force acting on this front wing from the, it's an upside down airfoil, so it's pushing it down against the ground. And we're going to have similar on the back. We've got the weight of the car. I'm using it as one big vector acting somewhere at the center of mass. That could include the driver, I suppose, in this case. And then we're going to have the normal forces at the four wheels, and that's the ground pushing up at the car. So this would be a pretty good free body diagram of this rigid body. These forces are not concurrent, right? Concurrent means all their lines of action intersect in a point, and this is not the case for this free body. If you've ever watched Formula 1, or if you watched anything really, you'll see, when things have moment acting on them, forces that are not concurrent, what can happen is things can flip. And that flipping really is due to the moment, because moment is really that tendency to cause rotation. Now, if you look here, you can see this 2D cable system. This is something like we would have covered in a previous set of slides. These forces are all concurrent. They all act through point B, which is some infinitesimally small little point there. And, if that ring were to break, it wouldn't really flip. I mean, it might flip after the energy releases it or whatnot. But I'm talking about like these forces that are acting on it like this are not causing this thing to flip or spin. And that's because they're all concurrent. So it's really all about these lines of action. So rigid particle has been a nice little simple system for us, and we'll still use it as the semester goes on. But in general, the more generic, the larger, more general case is the rigid body like you have over here. What is a moment of a force? What applications? Wrenches, pry bars, beams, really pretty much everything starts to have moments, and we're going to deal with moments a lot this semester. Okay, so let's look at the moment of a force from a 2D perspective. This is the most basic way to look at it. Here we have a wrench being loosened by someone. We're trying to turn this bolt counterclockwise to loosen it, lefty-loosey, righty-tighty. And so the worker is going to be pushing to kind of like to the right and down on our page, and that's going to loosen that bolt. And what's really going on here is we're creating this moment, which we'll call M sub O here, about point O due to this force. And the force F, if you multiply it by its perpendicular distance to the point in question, that's going to get that moment. If you have trouble, you're loosening this bolt and you have trouble getting it to turn, one thing you could do is put a pipe on the end of the wrench and lengthen the wrench. They call them cheater bars. And what that does is it actually increases the D, which is that perpendicular distance. And even if the force is the same, it's as hard as you can push, so your force is the same, the distance is going to make that moment larger. Likewise, if you wanted to keep the same moment, but but work less. You could put a cheater bar on there and then just push lighter because, if the distance is twice as much, then your force would be half as much. This is the same thing that you've been studying for, in past courses with torque. And so forces that are acting at a distance away from a point cause moment. And if they're causing a counterclockwise rotation about the point, then we usually say that that is a positive moment. And if it's causing a clockwise rotation about the point, we say that that's a negative moment. And this is about, again, the simple 2D scalar formulation of it. And we'll get into it a lot more detail. But moment really is just that torque that you've learned about in the past. The reason we have a different name for it really is it has to do with the technical side of things, where torques were really about creating angular momentum, and we're not really trying to change to angular momentum per se here. And then the word moment comes from, you'll hear it later when we talk about moment of inertia and second moment of area. Moment is when we say, well, we're dealing with an instance of a vector happening at some point away from another point. And so this perpendicular distance is what we call the moment arm. You can call it the lever arm and all these things, but this is really technically called the first moment of a force. But from here on out, you're going to hear me say moment. And that's going to be the name that you're going to hear in most engineering. We still use the term torque some. It'll be for, things that have long axes that we're twisting around the axis, like drive shafts and things like that. We still call torque, but all this other stuff we usually call moments, like this wrench. We're not twisting the wrench around this long axis. We're bending it about the other axis. So let's dive into this a bit more. Here we have some kind of point O over here with like some kind of bent bar coming off of it. That's got some height B and then some length A over here. And there's this force acting on it at some angle. Well, the moment about O would be that force times the perpendicular distance. That perpendicular distance you can see is right here. And what is that value? I don't know. I mean, you could figure it out. It's got a lot of math involved. And that perpendicular distance is the shortest, straight line perpendicular distance to the line of action of the force. But, that distance D can be hard to calculate. Think about it. You're writing all this stuff on the page, and when you do all this, like, sometimes this could be like so big it could go off your page depending on the angles. So this can get kind of cumbersome. So a nice way to deal with this is actually to break the force up into its components, its X and Y components, and then we can find the moments caused by these two forces. And that's because the moment of the resultant is equal to the sum of the moments of the components. So you could find the moment of F acting at this distance D, or you could break it up into Fx and Fy, the components of F. And Fx perpendicular distance would be right here, and that would be this distance B. And Fy would be acting up, and it would be at this perpendicular distance A. Now, an interesting thing to note here is, as I've got this drawn, righty-tighty, lefty-loosey, counterclockwise positive, clockwise negative, Fy here is going to be causing a counterclockwise or positive moment about O, and Fx will be causing a negative moment. You do both and you add the results together, and it's the sum of the moments. And if it ends up being positive, then it's counterclockwise. If it ends up being negative, then it's clockwise. Okay, so we can determine the direction of rotation by imagining the body pinned at O and deciding which way the body would rotate because of the force. And the way I like to do it is draw it on a piece of paper and put your pencil tip at O. And when I say on a piece of paper, not a notebook paper, but a loose leaf piece of paper so you can actually move it. But put your pencil tip at O and then push. Just give it a little nudge along the line of action in the direction of the force. And that the direction that it spins would be the moment, the direction of the moment as well.